Now for Coulomb's law, in all of its vector glory. No more magnitudes. So let's look at the real Coulomb's law. So we'll still have our two charges on an axis. Q1 and Q2 are the charges. And we're now going to call this 1, 2, R12. Okay, so R12 is the displacement between charge 1 and charge 2. The displacement if you go from 1 to 2. So the actual force that we want to calculate with Coulomb's law is F12. So F12, let's be clear what that means. F12 is the force Q1 applies to Q2. Okay? So F12 is experienced by Q2. It's applied by Q1. If you're going to draw it, you would draw it over here. F12, the force 1 applies to 2. It's equal to Coulomb's constant, Ke, just like before. The charges go up in the top, just like before, Q1 times 2Q times Q2. The separation goes in the bottom, R12 squared. So that's the same magnitude as before. We just have some extra notation to keep in mind who is applying force to whom. And then finally, we need the vector part. We need this to be a vector, and you do that with this thing, R hat 1, 2. Okay? So we have many kinds of hats here. We have vector symbols, we have nothing, and now we have this, R hat 1, 2. And this is a unit vector along the Q1, Q2 axis. Okay? It's a unit vector. It points from 1 to 2, and its magnitude is equal to 1. Okay. So this notation is also important for the unit vector because it tells you which way does the unit vector go. Well, if it's labeled R hat 1, 2, it points that way. Okay? And its magnitude is 1. What it does is it gives this a direction without changing the magnitude. Right? That's what this thing does. So you'll see these a lot in your physics book, and you'll see all it's doing is reminding you it's a vector. We have to say which way it goes. Okay? So let's look and see if this works, if this reproduces the repulsive attractive thing. So let's imagine that both charges were positive. Okay? So this one's positive, and this one is positive. Then if we look here, positive, 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 the separation is always, the displacement is always positive, you square it, everything's positive. Well, the force would be what direction? R hat 1, 2. So the force 1 applies to 2 is in the direction that points from 1 to 2. So R hat 1 to 2 looks like that. So for that charge, it did work out. When they're both positive, you get a force that's pushing away. But what about this one? Well, this one, the force would be F21. You switch everything. The force this one experiences, the force 2 applies to this one, is this way. F21. F21. And you plug in all the numbers, positive, everything's positive, but then the unit vector would also be R hat 21. Right? So also the unit vector is in the right way. And here, if I were to draw F, it'd be F12. So the way we're defining this unit vector, that it's along the axis, it points from the first number to the second number, makes the repulsive aspect work out. If one were positive, again, and say one were negative, well, you can see what would happen. The magnitude would be negative. It would point in the opposite direction as the unit vector. So 1, 2, the unit vector is still that way. The unit vector doesn't care about the charges. It's just to find by the geometry. But then F12 would be the opposite direction because of the negative magnitude. And here would be the same thing. The unit vector 2, 1 is still that way, but then the force would be this way if they were opposite charges. So you can see the way we're defining the unit vector does reproduce the attractive and repulsive for opposite and like charges. So unit vectors are important. They really do help you see which way a vector points, and we're going to play with them quite a bit more as we move along.